Hello and welcome to class 17. This is on the multipole expansion of the magnetic vector potential. And this is the second half of section 5.4 of the textbook. After we've defined the magnetic vector potential, we're going to define an expansion of it that makes it more convenient to use and is analogous to the multipole expansion of the electrical potential that we defined a number of classes ago. Remember, the goal of the multipole expansion is to characterize, in the case of our electrical potential, a charge distribution, how it behaves at large distances, whether it behaves like a monopole, a point charge, or a dipole or a quadrupole, what the dominant term is. And similarly here, we're going to characterize how not a charge distribution, but a current distribution behaves at long distances through the magnetic vector potential. Okay, so the multipole expansion, let's set up our geometry. So we have a loop of current here, and we choose an origin, and we have a distant point where we're observing the magnetic field, or the vector potential rather, and we let, that's R, and we let R prime, the source term, range around our loop. Now before, for the electric multipole moment, our loop R prime pointed to charge, so it was a dq prime here. Now we're pointing to dl prime, a length of current. And then we have the separation vector R, script R, between the R to the field point and R prime to the source point. Okay, so from the last lecture, we found that the vector potential of a current loop can be written in this form, mu naught I over 4 pi. Makes sense that this is a standard magnetic constant. Makes sense it's proportional to the current. And then what we showed last class is that it's equal to the integral over the loop of 1 over the separation vector times dl prime, integrated around the loop. dl prime being the length elements as we integrate around the loop. Okay, so we showed this last time. We made an argument for this last time. I won't get into this now, but we'll just start. This is our starting point here. So to simplify this and make it more useful, we're going to do an expansion in 1 over the separation vector. Now the separation vector involves, this is the separation vector between the source point and the field point. It involves the distance from the origin to the the field point, the distance to the source point, and the angle between them. So we expect the expansion to involve those 3 variables, and it does, and it's a bit complicated. This probably is slightly off-putting or slightly scary to see this full expression. But let's break it down. So the mu naught over 4 pi is still out in front. And it turns out that, so it makes sense that as the separation vector gets bigger, in general, the distance from the origin to the field point will get bigger. That turns out to go as r to the n plus 1. And then inside the integral over the loop, we have r prime to the n times this p sub n is a polynomial in the cosine of the angle between r prime and r. And then the dl prime is out in front. Okay, so I'm not requiring you to follow or understand this This is sort of graduate level mathematics or physics, mathematical physics. But I would like you to be familiar with the name of these polynomials. These are called the Legendre polynomials. And for those of you taking quantum mechanics right now, which is probably all of the current class and many of you in possibly in future classes, you'll find these Legendre polynomials also come up in the quantum treatment of the hydrogen atom. Okay, so they come up in various places where we're dealing with spherical coordinates and we're doing expansions, excuse me, expansions like this. So, so out of this, just take, don't get lost in the mathematical detail, just take out the fact that we're expanding in the separation variable. It involves two variables r and r prime, and it involves this set of polynomials. That's enough for this class. Okay, so let's get down to the actual terms and what they look like. In this sum, for n equals 0, we have r to the 0 plus 1, so we have 1 over r, and r prime to the 0 for n equals 0 is 1, and the first Legendre polynomial is 1, so we just get the integral of dl prime. Okay, and you can, if you want to think ahead or pause and think ahead, what would be the integral of dl prime over this entire loop? Okay, so you can pause and think about that for a second if you want. We'll come back to it in a second. Then the second term, for n equal 1, we're going to get 1 plus 1. So we get 1 over r squared, the integral of now r prime to the 1. And the first polynomial is the second Legendre polynomial, I suppose. The first order one, n equal 1, is just Pn of x is equal to x. So it's just cosine alpha dl prime. Here's the dl prime. And then the third one, you can see the pattern. The r increases by 1 in the denominator each time. The r prime increases by 1 inside the integral in the numerator, and we get a new Legendre polynomial, and they get more and more complicated functions of r. So this is, as for the electrical multipole expansion, this is the monopole term. This is the dipole term that goes as 1 over r squared, and this is the quadrupole term that goes, the potential goes as 1 over r cubed. Okay, so have you thought about that monopole term yet? What would this integral of dl prime over the loop be? Well, in fact, it's got to be 0, right? Because if we go all the way around the loop and you add up all of the little contributions, the little length changes, you come back around, since they're vectors, you've come back to where you started, and so you get 0. So that means that the magnetic monopole term is always 0. Unlike in the electric multipole expansion, where this was an integral over charge, and we could get a positive or a negative charge here, and so a monopole term. The magnetic monopole term is always 0. And that's connected to the equation we have, that the divergence, one of Maxwell's equations that we're building up, that the divergence of the magnetic field is 0. The divergence of the magnetic field being 0 can be shown to be equivalent to there being no isolated magnetic charges. So no chance of having a magnetic monopole, isolated magnetic charge. All right, so that's an important physical fact. Let's move on to the dipole term. So we'll just group some terms here, mu naught I over 4 pi r squared. And here's the integral. We're going to do a couple of mathematical manipulations here. R prime cosine alpha can be written as r hat dot r prime, because r hat dot r prime will be the length of r times the length of r prime times the cosine of the angle between them. Okay, so that's just another way of writing r prime cosine theta. And then we come to a somewhat curious relationship that says that the line integral of this r hat dot r prime dl prime can be written as minus the this unit vector cross product with the area, or the directed area, over this loop. Okay, and so I'm not going to prove this here, except to say it's proved. It's actually a problem, 1.62 in the fourth edition of the textbook, and except to say that it must have to do with Stokes' theorem, because we have a line integral being equal to the integral of something over a surface which is bounded by the line. Okay, we won't prove that here, but we're just going to use it. Okay, so we'll define, to use it, we'll define a new term which borrows this I here, which is sort of floating out here, times the integral, this integral of the area over the loop. This should really be dA prime here. But anyway, so the current times the integrated area is known as the magnetic dipole moment. And if it's a flat, like a disk or a square or a rectangle, it can just be a single A. If it's an irregular shape, we've got to integrate over the surface like this, do a surface integral. Okay, so that allows us to write the vector potential in a nice form, where we have, let's see, we bring the I from here over here, so we have I dA prime, which is M, our newly defined magnetic dipole moment, M. Then we have minus R cross M, but minus R cross M is the same as M cross R, because when you switch the order of a cross product, the sign changes. So we get M cross R, and we have our mu naught I over 4 pi R squared. Okay, so through this little derivation here, we have a nice expression, coordinate-free expression, coordinate system-free expression for the vector potential of a dipole. Okay, so nice expression here. Okay, so let's look at that in a nice geometry, where we take the magnetic dipole moment to be along the z-axis. With them directed along the z-axis, this becomes, so I've just repeated the equation from the last slide, m cross r hat over 4 pi r squared. And then if this is along the z-axis, m cross r is the length of m times the length of r hat, rather, times the sine of the angle between them. But here the angle is just the polar angle. We're in spherical coordinates. So we just get mu naught I over 4 pi times the length of m times the length of r hat, which is 1, times the sine of the angle between them, but that's the sine of the polar angle, over r squared. And then m cross r, if you use the right-hand rule, points in the phi hat direction. Okay, so this is in the spherical coordinate system. Now we have the vector potential of a dipole. And what's the purpose of the vector potential after all? It's to find the magnetic field. So let's go ahead and take the curl of the vector potential. And so we have to use one of our formulas for the curl in um, complicated formulas for the curl in spherical coordinates, but it can be done. It's straightforward. It's a little tedious, but it can be done. And we get this expression here, mu naught m over 4 pi r cubed. Makes sense because the curl is a kind of derivative, so the derivative of 1 over r squared is 1 over r cubed. And then we get terms in theta and sine theta in the r hat and theta hat direction, okay, perpendicular to the direction of the vector potential. Okay, so what does that look like? This strange expression. Well, it actually, hopefully, this looks kind of familiar. You've probably seen these patterns. If you put an iron bar down and you put iron filings, they'll line up and look something like this. So this is the field of a dipole. In this case, a pure dipole, meaning there's no contributions from quadrupole or octupole moments. So it looks kind of like a spider. And in fact, it has the same form as an electric dipole, except this represents a magnetic field and the electric dipole represents a electric field. So a pure dipole, a totally pure dipole field doesn't exist in nature. But if we take a current loop and shrink it, and then so one way to think of it is taking the separation of the two ends of the dipole and letting them go to 0 of the bar magnet and letting the magnetization in the bar magnet go to infinity. Another way is to think of a ring of current and letting the size of the ring go to 0 while the current goes to infinity in such a way that the product stays equal to a finite magnetic moment m here. So it's a limiting procedure, which is never quite realized physically, but we can approach this field. So a real physical dipole, which has a finite size, either a current ring or a bar magnet, is going to deviate from the pure dipole near the origin, where the actual physical object is, whether it's a current ring or a bar magnet. But you can see that far away, it starts to get closer, and these two start to get closer and closer together. So the physical dipole can be well approximated by a pure dipole as we move far away. Said deviation from the pure dipole field at small distances, and these corrections here would be represented by higher order terms, the quadrupole and octupole moments, and so forth. Okay, so this is a little bit unusual stuff, but just to summarize, we have defined for the vector potential, the magnetic vector potential, which is important in calculating the magnetic field. We defined a multipole expansion, analogous to the multipole expansion we defined for the electric potential. And the goal is the same for the two multipole expansions. It's to understand the long-range behavior of the potential and of the field derived from that potential. And we have identified here the most important term, the dipole term, and found a very nice expression for the vector potential of the dipole of a magnetic moment, which can be a loop of current or a bar magnet. And then we've recognized that the mathematical derivation of the field from that corresponds to what we've seen experimentally for the field of a bar magnet hopefully in previous labs. Okay, hopefully that gives you a taste of the mathematics, a taste of the physical intuition, and a taste of why once again why the multipole expansion can be useful. Thanks for your attention and see you in class.